Hey pals, Matthew Mr. Barnes here again, bringing another wicked awesome video. This is a seldomly made physics video, and this one particular is on Lorentz's force law, which is for a charged particle like an electron or a proton that is in a magnetic field. So basically what happens when an electron or a proton enters a magnetic field is that it experiences a force. And because that force, it changes the path. So I got a little simulation here, and I've got a negatively charged particle. So it's not an electron, but something a little bit smaller than that, in charge-wise. And you can see I've got a field that's coming straight out of the page. And I know, like, you would probably have learned your left-hand rule number 3. I know my students have. And we use left-hand rules, which is for electrons. If you're using a right-hand rule, it's for a proton. So it's kind of hard to demonstrate over a video, but I will attempt. So just as a recap, so this field, because it's dots, means he's coming straight out of the page. So your hand would align with the field straight out of the page. Try to focus the camera a little bit there. So straight out of the page. The direction of your thumb represents the path of the particle. So for example, my particle is going to be moving to my right. So if I flip my hand over, then my field is still coming out of the page, and my thumb, if I can do it, is pointed to the right of my screen. So I'm expecting that particle to go the direction of my palm. So my palm is facing straight up, so I expect that particle to go straight up. So let's just run the simulation and see what happens. So there we go. You can see the particle actually gets shot straight up, okay? So basically, it experiences a force. And actually, if you let this thing just continuously run, it would enter, UCM, uniform circular motion. So that's a good combination topic if you've done UCM already. And then, you might have, experienced that topic. So your teacher might throw something at you like an electron enters uniform circular motion, and you kind of got to hit on a couple different topics. So this is the formula we can use to actually calculate the force, the magnetic force, on an individual charge. So force as in newtons, and we've got the charge of an electron, so and a proton, and it could be a given charge. So something to remember: the charge. You can hear my daughter in the background there, guys. Apologize. We got a sick day this morning, so that's why I'm here doing this. The charge of an electron is 1.60 times 10 to the negative 19 coulombs. So obviously an electron would be negative and a proton would be positive. We don't concern ourselves with putting that negative into the formula because we want to know. We want to understand that that negative does not mean direction. That negative means a deficiency of or excess of electrons. So if it's negative, it has an excess of electrons. If it's positive, it has a deficiency of electrons. Then, of course, we have V, which is velocity in meters per second. And we have B, which is magnetic field strength in Tesla. And then, of course, we have sine theta, and we use degrees for this particular formula. So the first thing we kind of got to understand is that a proton and an electron will behave differently in a field. All right. So essentially, we use a right-hand rule for a proton, or we use a left-hand rule for an electron. So I've got that note written here. It says, recall that left-hand rule only applies to negative charges. So we got to keep in mind that the left-hand rule only applies, in our case, to electrons or something that's negative. I'm going to have to pause this video for 1 second, guys. And by the magic of YouTube, I am back. Sorry about that. I had a little issue with my 3-year-old. So, as I was saying, left-hand rule applies to negative charges. So, I've got 3 charges here going through a field that is coming straight out of the page. So what we want to do is we want to use our left-hand rule number 3 to be able to determine what's happening here. So remember that these x's, and see if I can write this here, x's mean into the page. So x's mean into the page. So the magnetic field for this one is into the page. So what we would do, I don't know if you can see my screen here now, but we can point our fingers into the page. So you can see my hand is pointing right into my computer screen, and if you have the paper in front of you, you would point your fingers directly into the paper. Doesn't matter which way your palm is pointing or which way your thumb is pointing. Right now it only matters what your fingers are doing, and the fingers represent the mag field. The thumb represents the direction of an electron. So all of our particles are traveling to the right. So you can see I point my thumb to the right, and then I worry about what my palm is doing. My palm is pointed down, therefore that's the force that an electron experiences. So an electron, when it enters this field going into the page, it's going to move down. So that means that R is the electron. So we don't really need to do the right-hand rule to figure out what a proton does. A proton is going to, well, the charge will be negative, obviously. So we don't know if this is electron, proton, but we're assuming electron, proton, neutron. And then we don't really need to worry about using the right-hand rule, because all we need to know for a proton is that it's going to do the opposite of electron. So if electron moves down, the proton is going to move up. So the proton moves up. So that's our P is the proton, just a fluke that it's labeled P. And then the middle one goes straight through the field. So that must be the neutron. All right. There it is. And that has no charge. So just an example of that. That's how, particles move through fields. So that takes care of three, big examples there. So let's have a look at an actual question where we have numbers, and let's look at using the formula. So he says we got an electron. So first thing, if I read an electron out to the side, I'm writing my Q. So my Q is 1.60 times 10 to the negative 19 coulombs. I do not put the negative in. I ignore the negative. So we have, so it's projected perpendicularly. So remember, theta perpendicular means 90 degrees. So that's 90. And if you get perpendicular, basically it means sine can be left off, because sine of 90 is 1. Into a magnetic field with a velocity. So usually these velocities are pretty high. 3.3 times 10 to the 7 meters per second. And experiences a force, so that's our F, of 1.3 times 10 to the negative 13 newtons. So the next thing we want to do is we want to write out our formula. So F equals QVB sine theta. I don't know why I'm using two different Q's. I'll fix that up. So I'll change this Q to a lowercase q. And again, if you want to use uppercase, lowercase, it doesn't matter to me. Might be, certain physics teachers might be particular, but that is not me. All right, so the next thing we want to do is we're solving for magnetic field. So magnetic field is B. So I'll put my B equals question mark here. And I prefer to rearrange these prior to putting the numbers in. And that's not always the case, but for these particular problems, you're always going to have those times 10s to the whatevers. So it makes life a lot easier if you just rearrange, and you don't have to worry about rearranging those big old times 10s to the exponents, right? So we're looking for B, and this equation's pretty easy to rearrange. We just divide everything that's not B on the right-hand side. So divided by Q, the V, and the sine theta. And then we do the same thing to this side, Q, V, and sine theta. And then we have B equals F over Q, V, sine theta. So the B is now here, and this thing is right there. So now we are good to go, and we sub in. So 1.3 times 10 to the negative 13 for our force. And let's see, for our Q, move this up a little tiny bit. For our Q, we end up with 1.60 times 10 to the negative 19. And then my V is 3.3 times 10 to the 7. And remember what I said about the sine? Sine of 90 can be left off. But if you're not completely confident in doing that, then just leave it alone, okay? So now I'm going to do this in my calculator, and depending on what type of calculator you have, you got to be very careful. My camera's just crapped out on me, so I was going to show this on the calculator, but that's all I can do now for now. So I put the 1.3 times 10 to the negative 13 in, and if you're lucky enough to have a Casio, you can do the over button. But if you are not, you want to just make sure that that entire bottom is in brackets, or you divide it, do multiple divide signs. So I end up with a field, and we're going with sig figs. We have 2 here. Remember that 90 does not count. We go with 2.5 times 10 to the negative 2 Tesla. All right? And it's always a good idea, which I'm going to do, is to double check this calculation, because with these numbers, it's so easy to make a little mistake, especially without, all those times 10s and things like that. You mess up a negative, you drop a negative, or you mess up an exponent, then you could easily make a mistake. Yep, just double check, so that's what I had. So that's a good first example of solving for the magnetic field, and really solving for V is much the same. It just changes a little bit how the formula looks. So I'll do an example now of solving for theta, finding the angle. All right, so let's have a look at this one. So again, we have an electron, so we know our Q. Q is 1.60 times 10 to the negative 19 coulombs. I'm going through a magnetic field of 1.50 Tesla, and it experiences a force of 2.40 times 10 to the negative 13 newtons. And it says, what is the angle between the electron's path, so that's theta, and the magnetic field lines? So again, we look at our formula. F equals QVB sine theta. So ultimately we want to solve for theta, but before we do that, let's solve for sine. So we got to keep the sign, everything else got to go. So divide everything by QVB, divide everything by QVB. So it's sine theta equals F divided by QVB. So let's go ahead and see if we can't find the value of sine theta, and then we'll go ahead and find theta after that. So we go 2.40 times 10 to the negative 13, all divided by, then we do our charge, which is 1.60 times 10 to the negative 19. We get our velocity, which is, let's see, velocity, did I write it down? No, I did not write it down, so it's 2.0 times 10 to the 6. So that's my lovely daughter in the background. She is the sweetest. 2.0 times 10 to the 6. And B is 1.50. So what we're going to go ahead and do is just basically do the math on this. And again, if you're doing this in a calculator that's not a Casio, then you want to make sure that this entire bottom gets those big brackets around it. Or you can just do everything divide. So 2.40 exponent negative 13, divide by 1.6 exponent negative 19, divide by 2 exponent 6, divide by 1.5, and that'll work exactly the same as using brackets. And if you do that, you get a really good number. You get let's see, you get sine theta, should be, anyway, it doesn't matter the color. Sine theta equals 0.5. Then if you know your exact ratios, you can do that, but we're not going to pretend like we do. So we do sine negative 1 to the 0.5 inside. So sine negative 1 means second function or shift on your calculator, and then you press the sine button. All right, so shift the second function, press the sine button. You've probably done it using Intrigue a billion times, and you end up with an angle of 30 degrees. All right, well, I hope this video was helpful to my students, and I hope to be back in class in the next couple days once my daughter heals up. Thank you so much for watching this video. As always, I'd appreciate it if you like this video. you could give me a subscription or subscribe, drop a like, drop a share, whatever you want to say. And thank you guys for watching, and I'll see you guys in class.